Hi there students, welcome to HSC Chemistry and the acidic environment topic. This particular video is going to focus on Le Chatelier's principle. So what we're going to do is have a look at reversible reactions. Now I've already sort of alluded to this with some of the work that we've done previously, but we've seen the sorts of reactions that occur between magnesium and oxygen as reactions that are single directional. They go to completion. So we have a couple of one or more reactants and they react together to form one or more products. And that process is a one-way process. However, there are certain types of reactions in which the reactants start to form the products, and then once the products reach a certain concentration, they will start to break down into the reformation of the reactants. And this is known as a reversible reaction because the reaction can go both ways, in the forward direction and in the reverse direction. What it also means is that at any given point in time, except at the very beginning, if we just start with reactants, we will have a certain concentration of all species reactants and products in our reaction vessel. The point that we look for is a point called the equilibrium. And at equilibrium, the important thing is the rate of the reaction, not the actual concentration or quantities. So when the forward reaction is occurring at the same rate as the reverse reaction, then we have reached equilibrium. So the important thing about reversible reactions is A, they occur, some reactions don't go to completion, and B, when the rate of the forward reaction is the same as the rate of the reverse reaction, then we talk about an equilibrium. And as I said, this is not about equal concentrations. In order for a system to reach equilibrium, there are a couple of important considerations. The first thing is it must be a closed system. The system must actually be contained. If it's an open system, such as in a beaker where maybe gases can escape, then it is no longer considered to be a closed system, and therefore equilibrium cannot be established. So the system must be a closed system in order for equilibrium to occur. There must also be no macro level changes occurring. So that may be color of the solution, that may be bubbling that's occurring, which may be occurring at different rates. It may be temperature change. Once any of those changes cease, or at least appear to cease, then there is a point where the system could have reached equilibrium. Okay? The key is that the concentration of the reactants and the products is no longer changing. But that doesn't mean it's not still reacting. All it means is that the rate, our third condition for equilibrium, is that the rate of the forward reaction is equal to the rate of the reverse direction. Okay, so that what is happening in one direction is also happening at the same rate in the opposite direction. So there's no net change in the concentration of the reactants or products. Now, we have sort of briefly talked about equilibrium systems before, but the important thing now is Le Chatelier's principle. And it's not just what this principle is, but it's how we apply it. And the key to this is how you apply Le Chatelier's principle. So this is Le Chatelier's principle, paraphrased. When a system in equilibrium is subjected to a change in concentration, temperature, external pressure, or some other factor which upsets the equilibrium, the system reacts in such a way as to counteract that change. So if we were to summarize the key components of Le Chatelier's principle, first of all, the system must experience some change. This change must upset the equilibrium. It must cause some effect on the equilibrium system. And then what happens seeks to counteract that change. And there is a couple of ways in which this can happen, so let's have a look at an example. Here's an example of an equilibrium system between colorless dinitrogen tetroxide and brown nitrogen dioxide. Each of these can exist in a closed vessel, so obviously it's going to have to be a closed vessel if equilibrium is going to occur. And therefore we will have both species existing. You can also see from the way that this is written that this has a positive delta H value. A positive delta H value means the forward reaction is endothermic. So it would actually get cool. Now, what are some of the ways that we could change this system? Well, we could add more N2O4. What would that do? If we add N2O4, we increase the concentration. That's the change. That will affect the equilibrium system because now we have more of the first of the reactant of the first species, and therefore the system will change in order to counteract that change, which means the system is going to shift to the right. That is going to lower the concentration of N2O4 and increase the concentration of NO2. What's another thing we could do? We could heat the system. If we heat the system, we increase the energy. If we increase the energy, then there is more energy in the system, and the system will shift in such a way. This is the change. How will the system shift to counteract that? Well, if it is an endothermic reaction, that means that it'll absorb heat to produce more of the, in this case, product. So again, the system will shift to the right, and we will have an increase in the concentration of NO2, which will absorb that extra energy. A third thing we can do is we can increase the pressure. Okay, so if the pressure goes up, then effectively what we're doing is pushing all the particles closer together. They're going to bash into each other more often. Now, if that happens, this again is the change. Can we expect some shift in the system? Well, yes, we can. If you look at it, both of these species are gases, but every 1 mole on the reactant side will produce 2 moles of reactant molecules on the product side. So if we increase the pressure, what we want to do is we want to shift towards less gas moles. So this means that what we want to do, one way of counteracting that increase in pressure, is to reduce the number of particles, to reduce the number of moles of gas. This is actually going to shift the equilibrium in the opposite direction. We're going to decrease the amount of NO2, and we're going to increase the amount of N2O4. So we actually have less molecules, less moles or less molecules. So these are some of the ways in which Le Chatelier's principle can be applied in an equilibrium system. Of course, if this system were an open system, then we wouldn't be able to reach equilibrium. And there are certain things that we could do to this system, such as adding a catalyst, which wouldn't have any effect on actually changing the equilibrium. So the key to Le Chatelier's principle is we must have a change. That change must affect the system in some way, and then the system must alter in some way to counteract the effect of that change. So here's a question from the 2013 HSC paper, in question 24A. Consider the chemical system below which is at equilibrium. X gas plus Y gas gives Z gas plus heat. Plus heat means the delta H value must be negative. Explain the effect of decreasing the volume of the reaction vessel. Well, if we decrease the volume of the reaction vessel, we're going to increase the concentration of all the species. Okay, so the concentration of all of them is going to go up. But another consequence, if we keep the temperature the same, of increasing the volume, decreasing the volume, will be an increase in the pressure. And if the pressure increases, then the system will shift to favour less moles or less molecules. And of course, we do mean gas molecules whenever we talk about changes in pressure. We can't squeeze liquids and solids particularly well. But we can with gases, we can compress them, we can push them closer together. And if we've got an increase in pressure, then what we want to do is favour the smaller number of moles. So on this we have coefficients of 1, 1 and 1. So that means there's 2 moles of gas molecules on the reactant side, but only 1 mole on the product side. And therefore the equilibrium will shift to the right. It will favour product, and we will have an increase in the concentration of Z and a consequent decrease in the concentrations of X and Y. Thanks for watching.